The following problems are hard. The antiderivatives are either inverse trig functions or natural log functions, or both, and often you have to force the function to look like something that you know how to integrate. For example, in the first problem, we have the integral of 1 over the square root of 1 minus 9x squared dx. Now we should recall that the integral of 1 over the square root of 1 minus x squared dx is equal to arc sine of x plus c. So these two things should be related. So since these two things are related, we kind of have to figure out how to make this work. So in order to make this work, what we want to do is we're going to want to make this look as much like the integral of 1 over root 1 minus x squared as possible. So in order to do that, what I'm going to do is I'm going to make 9x squared into 3x, the quantity squared. So if I do that, now what I end up with is I end up with something where I can make a pretty simple u substitution. So u equals 3x and du equals 3 dx. And so now what I end up having is I have the integral with a 1/3 on the outside because dx equals 1/3 du. So I have 1/3 times the integral of 1 over the square root of 1 minus u squared du. And I know that that is 1/3 times arc sine, or inverse sine, of u plus c. So my final answer after I resubstitute will be 1/3 arc sine of 3x plus c. So that's the first problem. Second problem. I know that this looks a lot like the integral of 1 over 1 plus x squared dx. So these are similar. And because they're related, I kind of have an understanding of what this might look like. I know that this is arctangent of x plus c. So what I'm going to do is I'm going to want to make this look as much like the thing that we know as possible. So let's keep that in mind. So in a problem like this, I can't just take what I did in the previous problem and have this 9x squared turn into a 3x, the quantity squared. So what I'm going to want to do is I'm going to want to somehow convert this 9 into a 1. And the way that I convert a 9 into a 1 is by multiplying the numerator and denominator by 1/9, or I can multiply the top and divide the top and bottom by 9. So this is why on the top of your sheet it says force the 1 in a box. Essentially what you're going to want to do is you're going to want to force this number, this 9, to be a 1. So let's make this the integral of 1/9 over 1, because 9 divided by 9 is 1, plus x squared over 9 dx. So basically what I did was I took this problem and I divided both the numerator and denominator by 9. Now I can rewrite this x squared minus 9 to be, I'll move the 1/9 that's in the numerator to the outside. So I have 1 over 1 plus x over 3 squared dx. And now that I have that, I can make a u substitution and move along from there. So since u equals x over 3, du equals 1/3 dx, so dx equals 3 du, and now I can just move along from there. So this will equal 1/9 times 3 times the integral of 1 over 1 plus u squared du, and this looks a lot like what I wanted to find in the first place. So this equals 1/3 times arctangent of u, and u was x over 3, plus c. So that is the answer to the second problem. Problem 3. This looks a lot like the integral of 1 over the absolute value of x times the square root of x squared minus 1 dx, which we know is the inverse secant or arcsecant function. So our main objective is going to be to get it to look something like this. So if that's our objective, what we're going to do is we're going to have the integral of 1 over x. This would be kind of a restricted domain situation here. Uh, the square root of 2x squared minus 1 dx. So we're going to make a u substitution. U equals 2x, and du equals 2 dx. So that means I'm going to replace with du over 2. Dx gets replaced with du over 2. So I have 1/2 times the integral of 1 over x times the square root of u squared minus 1 du. Clearly this is not good right now because I have an x and a u in the same problem. So I'm going to replace this x with u over 2 because x is the same thing as u over 2. So in that case, how do we get rid of that and make it look like a u? Well, if I have a 1/2 in the denominator, that's the same thing as having a 2 in the numerator. So I have a 1/2 on the outside, and then if I'm dividing by 1/2, that's the same thing as multiplying by 2. So I can take this 1/2 and turn it into a 2 up top. So 2 times 1/2, those are going to cancel out, and I'm just going to get 1. So this is the integral of 1 over u times u squared minus 1 du, which is secant inverse or arcsecant of u plus c. That's the same thing as the arcsecant of 2x plus c. And so that's our answer. We actually could have done this problem another way. It's a lot more complicated. But if we take this to be u equals root 4x squared minus 1, we can do du and do a bunch of simplifying to get dx equals du times root 4x squared minus 1 over 4x. So I replaced dx with that. I did a little simplifying and I ended up with 1 over 4x squared du. Now notice that 4x squared is the same thing as u squared plus 1. So I can replace 4x squared with u squared plus 1. And this looks a lot like arctangent. So notice I can get two different answers for this problem. I got arcsecant of 2x plus c, or I got arctangent of root 4x squared minus 1 plus c. You should be able to show that both of these are equivalent, and I will really quick. So if I have, for example, let's just make it in the first quadrant. If I have a triangle where the secant is 2x, that means that by the Pythagorean theorem, I'm sorry, if the arcsecant is, I'm sorry, if secant is 2x, that means that tangent has to be, by the Pythagorean theorem, the square root of 4x squared minus 1. So these should be equivalent. Problem 4, dx over x squared minus 2x plus 2. This, at first glance, looks absolutely nothing like the other ones. And what we might want to do is we might want to make this into a natural log problem, or do a u substitution on the denominator. But if I do a u substitution on the denominator, I'm going to get du equals 2x minus 2 and then I'll have the integral of u du, and then I also have this 2x minus 2 in the denominator, and I can't really solve that given our u that we already had. This is not going to work very well. So because it's not going to work very well, I have to try another method. And the method that I would recommend is, if you can't get a u or anything, try to make it look like something that has an inverse trig function. So we might want to complete the square on the denominator. If you complete the square on the denominator, you end up with x squared minus 2x plus something. So if I complete the square, reminder, I take this number, I divide it by 2, and then I square it. So negative 2 divided by 2 is negative 1. And when I square it, that's 1. So since I added 1 to the denominator, I also have to subtract 1 from the denominator. So after I complete the square, I end up with 1 over x minus 1 squared. Notice that this entire thing is x minus 1, the quantity squared, and then plus 1 dx. This looks a whole lot like arctangent. So if I make u equal to x squared, or x minus 1, du equals dx, this is a really simple substitution. I get u squared plus 1 du, and so this ends up being arctangent, or tangent inverse, the inverse tangent function, of x minus 1 plus c. This problem. This looks like it might be able to be forced into something that looks like an arc sine, but I have to make a u substitution first. So let's say I make u equal to t to the fourth. So du equals 4t cubed. Oh, no, that might not work. Because if we look at this problem, what's going to end up happening then is, if I make this substitution, I have the integral of, at the moment, t over the square root of 1 minus u. And remember, to make it look like arctangent, I'm going to want this to be a u squared inside of the square root. Also notice that if I make this choice, what ends up happening is I have this 4t cubed, which when I divide, I'm going to get rid of one of the t's, but then I still have a t squared in the denominator, and t squared is equal to the square root of u. It just ends up kind of being messy. So let's make a different choice for our u substitution, and I will make the choice t squared equals u. So in that case, du equals 2t dt. So if I want to replace dt, I have du over 2t. So what I have here is 1 minus u squared inside of a square root. The t's are going to end up canceling. So the t that was in the numerator is going to cancel with the t that's down here, and I end up with a du. So I end up with a du over here. And then there's a 1/2 that goes on in this problem. This is just arc sine of t squared plus c. And don't forget, we have the 1/2. So it's 1/2 arc sine of t squared plus c. Once again, just a reminder, you can always check your answer by taking the derivative of what you get. So if you take the derivative of what you get, you have 1 over 1 minus t squared squared. That's inside of a square root. And then we had a 1/2, so don't forget there was a 2 here, times the chain rule, derivative of the inside, that's 2t. So the 2's are going to cancel, and I end up with t over the square root of 1 minus t to the fourth. So taking the derivative ends up proving that I was right. Problem 6. This problem is really hard, so I'm going to try and take this one a little bit slower. If I look at this, I have an x squared in the denominator and an x in the numerator. So what I'm thinking when I do this problem is I might have a u substitution instead of maybe a inverse trig situation. So let's make u equal x squared plus 6x plus 13. So du equals 2x plus 6 dx. Now in this situation, that means dx equals du over 2x plus 6. Now if we take a look at this, what we realize is that 2x plus 6 is not 2x, but it's pretty close. So what I'm going to do is I'm going to rewrite this problem, and this is kind of tricky. I'm going to rewrite this problem as 2x plus 6 minus 6 in the numerator. Now notice that's exactly the same as 2x, but it's rewritten in such a way where I'm going to be able to manipulate things. So in the denominator, I still have x squared plus 6x plus 13. Now if I do this, I can use some of the rules of integration to rewrite the integral as 2x plus 6 over x squared plus 6x plus 13 dx minus the integral of 6 over x squared plus 6x plus 13 dx. So I'm just rewriting 2x as 2x plus 6 minus 6 because I'm allowed to add 0 to any problem that I have. And then I separated the integral into two separate integrals. Now if I take a look at this u substitution that I did earlier, what I can do is I can now rewrite the first integral as the integral of 2x plus 6 over 2x plus 6 times u du, because I made this substitution in for dx. That's going to become the integral of 1 over u du. Now, let's take a look at the second integral. If I have 6 on the outside, I'm just going to rewrite that. I now have 1 over x squared plus 6x plus 13. This one does not have an x in the numerator anymore. So what I'm thinking now is I'm thinking this one is a lot like the previous problem, or two problems ago, where I had an x squared minus 2x plus 2, and I did a complete the square situation. So this part of the problem, I'm going to complete the square. So I'm going to end up with minus 6 times the integral of 1 over, sorry, I forgot the dx, 1 over x squared plus 6x plus blank plus 13 minus blank. And so 6 divided by 2 is 3, and then when we square that, that's 9. So we're going to add and subtract 9. So I can rewrite this as the integral of 1 over u du minus 6 times the integral of 1 over x plus 3 squared plus 4 dx. Now this one, again, it's pretty complicated. I'm going to move it up on the screen. So now if I'm looking at the one on the left, I can just do natural log of the absolute value of u, and u, remember, was x squared plus 6x plus 13. So now I've taken care of that left integral. Now I'm going to start working on the right integral, and this is a situation like earlier. We're going to go way back. We had this problem where we had to force the 1. So what I'm going to do is, this looks a whole lot like arctangent, but I need to force the 1. So this 4, I'm going to have to divide everything by 4, basically. So I have 6 times 1/4 over x plus 3 squared over 4 plus 1. So I'm dividing the entire, the numerator and the denominator by 4. So I have the natural log of the absolute value of x squared plus 6x plus 13 minus 6 over 4, which is 3 halves, times the integral of 1 over, I'm going to write this as x plus 3 over 2 squared plus 1, because 4 is really 2 squared, so I can write that as x plus 3 over 2, the quantity squared. Now that we can integrate, so I have the natural log of the absolute value of x squared plus 6x plus 13, and that one looks a whole lot like arctangent. So I can make a u substitution over here. So u equals x plus 3 over 2. Du equals 1/2 dx. So dx in this case is equal to 2 times du. So when I make a substitution, I have 3 halves, and then I have another 2. So I'm multiplying this by 2 times the integral of 1 over u squared plus 1 du. So my final answer will be the natural log of the absolute value of x squared plus 6x plus 13 minus 3 times arctangent of my new u, and in this case my u was x plus 3 over 2 plus c. That one's long and hard. Finally, I have a definite integral of this particular problem. This one, I have an x squared in the denominator and a 1 in the numerator, so I'm thinking arctangent. I'm going to try and complete the square. If that doesn't work, then we have to deal with some crazy natural logs, so hopefully this is going to end up working out. So I have the integral from 1 to 3 of 1 over x squared minus 2x plus blank plus 5 minus blank. So negative 2 divided by 2 is negative 1, and if I square that, I get 1. I keep on forgetting my dx's in this video. That's bad. So the integral from 1 to 3 of 1 over x minus 1 squared plus 4 dx. So once again, I'm going to have to force the 1. So I need to take this 4 and figure out that I need that to be a 1. So I'm going to divide everything by 4. So I have 1/4 in the numerator. I have x minus 1 over 2. I'm going to skip a step because if I divide that by 4, remember that's the same thing as dividing by 2 squared. So now I'm going to make a u substitution on my arctangent interval here, or integral. So I have du equals 1/2 dx, which means dx equals 2 du. So I'm going to have 2 times the integral. Oh, sorry, I forgot that there was a 4 over there. So it's 2/4, which will end up being 1/2, times the integral of 1 over u squared plus 1 du. So let's continue to simplify this. So I get 1/2 times arctangent of x minus 1 over 2. I'm evaluating this from 1 to 3. So if I evaluate this from 1 to 3, I get 1/2 times arctangent of 3 minus 1 is 2, divided by 2 is 1. So that's arctangent of 1 minus 1/2 arctangent of 0. And so we have to know what arctangent of 1 and arctangent of 0 are. So arctangent of 1 is pi over 4. So arctangent of 1 is pi over 4. When I have 1/2 of that, that's pi over 8. And then arctangent of 0 here when it's 0. So my answer is pi over 8.